Questions? Any comments? Any suggestions? Yes.
Before you start, can you explain again what that you've written?
So the G function, like let's go back. So our goal was to calculate the total intensity of light, right? Like this is what we called, like, I think I wrote the definition here. Total energy which is detected in your detector, and your detector can like split different frequencies and tell which one has how much contribution. So total energy in interval mu, nu to nu plus d nu, is equal to two components. The first one is the average of each mode. I call each frequency a mode. And the second one is total number of modes, right?
Yes, but what does the internal mu mean?
What does?
Internal mu mean? Right?
So like, I think it is helpful to go back to like the empirical result and try to see, like, here's the black body radiation that we are trying to make sense.
Okay, but my question is the frequency discrete?
No, it's not. We are like looking at continuous spectrum of frequencies, right? This is like a continuous spectrum. Any frequency is allowed, but the point is not all frequencies are equally probable, right? Your question, what does this G function do, is it's counting how many modes I have at the given frequency mu. And we'll derive this later. At the moment, I think it's not important where it comes from. You'll see it's not it's a simple derivation. All right, so last time we talked about photoelectric effect. Let me just take this exact experiment and ask if it's even possible to reverse the photoelectric effect. So the question is, is the reverse, hopefully you can see that, of photoelectric effect possible? What I mean is, like, rather than sending light to generate current, is it possible to generate current like this? You just shoot the electrons and expect light to come out like that. Okay, and the answer is yes, and this is what we call X-rays. Okay. So this is first observed in 1895 by, does anybody know the name? By Röntgen. And basically the idea is, like, if you shoot a piece of material like a metal or tungsten, for example, with like high-speed electrons, maybe I can just zoom into here. So here's the inside of material. I don't know, there are all these nuclei, there's, like, I don't know, some complicated material inside, and my electron here is entering this medium. As it travels inside, it's going to collide with nuclei or some other particles inside, and as it does that, it's going to slow down. But we know when a charged particle slows down, so this is charged particle slows down, which means there's like an acceleration of charged particle, like E, which is charge, with a non-zero. We know what happens, right? If I have a charged particle and I give like a acceleration, everybody here took physics 105. What? Exactly. Radiation comes out. And there's like a name for this one. This is called Bremsstrahlung. And this means in, I think, German words, I've been told it means braking radiation. Bremsstrahlung. I may not be pronouncing it right, but I just repeat what I heard. Bremsstrahlung. You know German?
No, I just wanted to get used to it.
Okay, yeah. I think it's hard to say, but I just do the impression of its pronunciation. I don't know how it's actually properly pronounced. Okay? Yes?
Is the frequency of the radiation always in the spectrum of pixels?
Now we'll come to that, yes. Like, the question is, what is the spectrum, right? So let's remember, if you remember the photoelectric effect, there was like, okay, here's our spectrum. So this is like intensity. If you remember in the photoelectric effect, we looked at this as a frequency, sometimes omega, sometimes mu. But for whatever the reason, your book switched to wavelength here. And if you remember, okay, let's go back and see. So you can see here as a frequency, there's like a threshold voltage. Exactly like that. If you write it in terms of wavelength, you need to reverse this graph. And the intensity is going to have like a threshold, right? There's like, maybe I need a little bit room. Let me write it here. There's like some threshold. Oops. And it just goes up and shoots down. So this is, if you shoot electrons with, what do? We shoot electrons with something called cathode ray tube. We give the voltage and electrons are bombarded, and the amount of voltage we gave is going to determine how fast the electrons are bombarded. So this is, for example, V is equal to 40 kilovolt. This is like a huge energy, if you didn't know about kilovolts. So this is some lambda min. If you like change the voltage, like say this is like something like that, this is V is equal to 30 kilovolt. And if you change it even more, so this is V is equal to 20 kilovolts. So this is, for example, for tungsten target. And empirically, it was found that this lambda min was equal to 1.24 times 10 to the minus 6 volt times meter divided by V. Whatever V you have, it's going to change with that. So you can take V on this side, lambda min on this side, and you can kind of see V is proportional to frequency, right? V is proportional to nu. And the question is, what happened? Something is missing here. Does anybody know? In the photoelectric effect, the work function, right? What happened to phi? Anybody? So the answer is like phi, you can put it in, but it is like so tiny. What was the work function we found? It was 1 to 2 electron volt, depending on the metal. But here we have like gigantic energy, 40 kilovolts. So basically a tiny addition on this side doesn't matter. So we just omit that. So phi is of order, okay, phi is of order of 1 eV, whereas here the kinetic energy of electron is of order of 10 to the 3 eV. So you can forget about work function. Then what we have is like from the photoelectric effect, E times V is equal to H times mu max in the Einstein experiment. And this is going to translate to hc, right? Like nu times lambda is equal to c. This is light. This is how light travels. Then I can write things either in terms of nu or lambda, and this is going to translate to hc times lambda min. And okay, if you take this E on this side, and if you calculate H is the Planck's constant, which is now a fundamental constant of nature, like electron charge, and C is speed of light, fundamental constant, and E is also charge, which is fundamental constant. If you put all of these things, you are going to find 1.24 times 10 to minus 6, and the unit is going to be volt times meter. Exactly like the experimental result. Any questions? So let's remember photoelectric effect. So why do we need lambda min? And if you go back to photoelectric effect, in the photoelectric effect we said like we can model the metal like this, like a sea of electrons. So there's like a sea of electrons here, and because electrons stay inside the metal, right, they just don't flow out of metal. Something must be keeping them inside, and Einstein modeled this with like this potential barrier. There's like a little bit of barrier, just like in a bucket, like in this bucket, this water is not flowing out because there's like a potential barrier, right? And there is like a minimum frequency, and this minimum frequency should provide the minimum energy here. So this is delta E, actually, which we called phi. This phi, by Planck's equation, should come with h nu, and the minimum amount you have, we call it h min, right? That makes sense. And if you translate this to lambda, it is exactly like that. There's like a okay, this is minimum, and I think this should be I think for some reason I have also lambda minimum. Oh yes, exactly like that, right? If there is like a threshold for nu, there is also a threshold for lambda, and that is the threshold of this. And in the black body spectrum, we had something like that, right? This is like a voltage, or there's also in terms of like this. If you want, we are going to translate this threshold to h nu, and h nu is going to be h c over lambda, and that is going to determine this lambda min. Okay. Uh-huh. In the end, can you say one more time? I couldn't catch. Uh-huh. Work form of energy will be less and less. I mean, like exactly like so. The way I look at it is like photoelectric effect is X-rays are inverse of photoelectric effect, and you can think about in the photoelectric effect, there is like a range of frequencies. Your electron will not see anything, right? It wants to radiate, but it wants to radiate this energy to somewhere. So, right, for the electron to like give up that energy, it has to match the properties of your medium. It's not like, oh, like I have this extra energy, like take it. In the quantum world, that doesn't work like that, right? And to match that, you need to have like a threshold. Anything beyond that, it cannot give up that energy. Any other questions or comments? So I want to, okay. From this calculation and the energy of like this like kilovolts, you can also calculate the wavelengths of X-rays. Wavelength of X-rays happens to be lambda is order of nanometer to angstrom. Okay, so it's if you remember, like photoelectric effect which takes place in the visible range is 100 nanometer, right? 100, 500, 600 nanometer. For example, green light is 500 nanometers. And with green light, which is the visible, we can do double slit experiment, right? Because we can easily manufacture a double slit, which is order of 500 nanometers, which is, if you want, a little bit below human hair, right? Order of human hair. But like my question is, okay, here's the question. Is it possible to perform or do double slit experiment with X-rays? Can we do this? And by our like experience from like visible, we know this thing should be order of wavelength, right? Anything beyond that, it's not going to be a good double slit experiment. The question is, can we manufacture a double slit which is of order of wavelength of X-rays, which is of order of angstrom? Anybody want to take a shot?
Why not?
Like, can you, like, what is the required separation for angstrom? Like, if I ask you to give me something of order of angstrom in entire physics, what should you think of? What's that? Atoms, right? It is of order of size of atoms. Can you make a slit of order of size of atoms?
There's something called X-ray diffraction.
But X-ray diffraction is not done with double slit, right? That's where we are trying to get to. Maybe I'll give you the answer. The answer is you cannot do double slit, but you can do X-ray diffraction. Why? Because in materials, there's this nice crystal structure, and the separation between atoms is of order of atomic size, which is angstrom, right? And the idea is to use, okay, answer to this question, use crystals to get diffraction. Does that make sense? Right? Okay. So let's think about that. Think about X-ray diffraction. So the experiment is something like that. You have like a electromagnetic wave coming in, and you have like a sample. Let's say this. This is sample, and some electromagnetic wave is scattered, and we want to model this. And how do we model this? We model this as follows. Like here inside this material, there is like a periodic structure of atoms, and we can think of these atoms like this. For example, this one, and 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 this one, right? And we can kind of think about these arrangement. Like this is like a gigantic sample. There are like a 10 to 20 of these atoms. And we can model these atoms like these planes of atoms, right? There is like one plane, there is another plane, and there's another plane. Now I sent X-ray. Suppose this is my incoming X-ray, and it scatters from one layer, and it goes like that. And there's going to be like, okay, this X-ray is like a wavefront. There will be a second X-ray coming, and there will be reflected, right? Something like that. And what is the separation here? So this is of order of A, which is angstrom. I will call it like lattice constant of this sample. And you can see here, okay, I just have this and this. From here and here, this, okay, this is beam 1, okay, this is 1, beam 2. You can see beam 2 is a little bit behind because there is like extra path for beam 2 to take, so there will be a shift. And we know whenever there is like an extra path, there will be like an interference because these are waves and they can constructively or destructively interfere if there is like a path difference. So in the X-ray community, like you have to remember that sometimes, okay, a logical physicist would define this one to be the angle, but X-ray spectroscopists use this one. So there's nothing I can do about that. So this is the theta. If that is the theta, so this is perpendicular. So this is 90 minus theta. This is also theta. If this is theta, this is also theta. And I want to calculate the total. Okay, this is delta x1. This is delta x2. So delta x1 is equal to delta x2 is equal to, from theta and a, I can calculate, right? This is what? A sine theta, right? And total path length difference, let me call this L, is 2 times A times sine theta. And if this is equal to n times lambda, yes, and I have, okay, this is the condition for constructive interference. Then my result is 2a sine theta is equal to n times lambda. So this is, I think, called Bragg law or Bragg's equation. Okay, any questions? So basically, you cannot do double slit experiment, but you can still do the interference experiment. And this interference experiment is going to give you an idea about your sample. Right? By just looking at the interference pattern, by counting the fringes, you can actually deduce lattice spacing. And from that lattice spacing, you can deduce the structure of the material. However, there is one more thing. When you do the experiment with tungsten, you are going to have this. But when you do the exact same experiment with not tungsten, but say molybdenum, let's come to molybdenum. So you have, okay, I think we can just forget about all of these. Let me just skip the one in the middle. So forget these. What you are going to find is not only this Bremsstrahlung spectrum, but there will also be like these peaks like this. This is what I call K line. And okay, this is not tungsten anymore. This is molybdenum. And if you increase a little bit, there will be another line like this. This is what I call L line. These ones are harder to understand, but we are also going to understand. So in these ones, you need to understand the atomic structure. Not the crystal structure, atomic structure. And if you send the beam in the right energy, you can excite the electron of an atom, right? And when this happens, you are going to have like an extra peak. And if you go a little bit higher, you are going to like hit another energy level. And if it's the case, you are going to have another peak. Hopefully, we are going to see these two. They are going to be explained perfectly with quantum theory of atom. Okay, any questions? So these things are kind of like taught with wave nature of radiation or light. Let's now think about an experiment that supports the particle nature of light, and that's called Compton effect. Compton scattering. All right. And this time the experiment is something like this. I have incoming radiation, right? This is light in. There is like a standing electron. This is here E. Normally, if light is a wave, it should just pass through, right? It's not like billiard balls collide, not waves. But if wave is particle, we expect this wave to head-on collide with this electron, and there'll be, so this is light in, this is light out, and this electron is going to also electron out. This will also scatter. And I want to, let me call this, so this is the line. So this one is, let me be consistent. So I want to call this phi. I want to call this one theta. And all we need to do is to work out the kinematics. And in the kinematics, there are two things, conservation of energy and conservation of momentum. So on this side, energy from the Planck's law, h nu, right? And momentum, E, if you remember relativity, m was equal to 0, then E was equal to pc, then P is equal to E over c. On this side, we have E is equal to h nu, but there must be a difference in energy, so that difference in energy should go to electron. So I'm going to put h nu prime here, and here P is h nu prime over c. And for the electron, energy is, does anybody remember? I already give you the hint by opening up the square root. So this is P squared C squared plus m squared C to the fourth. And P is equal to P. I'm going to just use P for electron. So there I'm going to write three conservation laws, two for momentum in x and momentum in y direction, and one for energy. In total, three conservation laws. Let's do that. So momentum along x. So the coming light has h nu over c momentum, which should be equal to the projection of photon momentum, which is h nu prime over c cosine phi plus and p times cosine theta. This is the electron momentum, right? The second one, momentum along y is 0, right? There is nothing in the y direction in the incoming, and this should be equal to h nu prime over c sine phi plus p sine phi. So this is equation number 1, this is equation number 2, and lastly energy conservation. The incoming energy is h nu. Anything else? Do I have any other form of energy before the collision? Should I pick someone randomly and ask, or is, yes?
MC squared.
Yes, thank you. So this is mc squared. There's the rest energy of electron. And after the collision, we have h nu prime plus p squared c squared plus m squared c to the fourth. And this is the equation number 3. So I want to eliminate as many variables as I can, and I think there are different ways to do this, but I would like to do it like, if you see, there are like p cosine and p sine. I want to take these on the same side and take the square of both sides, and when I sum squares of p cosine square and p sine square, it's going to be 1, and I'll eliminate theta variable. So let's first do that. So p square cosine square theta is equal to h square nu square over c square plus h square nu prime square over c square cosine square phi minus 2 times h nu over c, h nu prime over c, cosine phi. So I took the square of first, and I left p cosine theta alone. And I do the same thing here. P square sine square theta is equal to h square nu prime square divided by c square sine square phi. Let's sum these two equations like this. Then p square is going to be equal to, I have h square nu prime. Okay, maybe I show you with this. So I have this term, and I have this term. This is also cosine square plus sine square, but for the angle phi. So this is going to be h square nu square over c square. I wrote this one, plus h square nu prime square divided by c square. I wrote these two, minus 2h nu over c, h nu prime over c, cosine phi. Good. Now for the p squared, I'm going to use equation number 3. So I'm going to leave this square root alone and take its square, and it's going to give me an identity for p squared. Let's do that. Actually, I can just write it. So p squared c squared plus m squared c to the fourth is going to be equal to h nu minus h nu prime squared, which is h squared nu squared plus h squared nu prime squared minus 2h nu prime. So I take the square of first one plus the square of second one, m squared c to the fourth, and the cross term. Let me push this a little bit. I just need one more term, and that term is going to be, right, m c squared h nu minus h nu prime. Again, unfortunately, I expect you to be able to do these calculations. You know, I don't like doing this, but we have to do this. Then, so here is mc square. Okay, let me use color. So this one is gone with this one. And I can divide everybody with c squared. Like, let me write this c squared, let me write it like c, and this one will go, and this one will go. Now I can put this p to here, right? I have something in terms of h mu's and h mu primes. I have something in terms of h mu's and h mu primes. And if you can follow, if I put this line on the left-hand side and this line on the right-hand side, this one is going to cancel with this one. Is that clear? Hopefully, right? So this one is going to cancel this one. Oops. So this one also cancels. And what remains is, let's write what remains. M, I don't like this color. M, I think this M should be, okay, let's keep it. If there's a mistake, we can fix it. H nu minus H nu prime is equal to, so this term, I'm going to write it on the other side. I think there is like a 2 here, right? So let's go back and fix this. I am taking the square of this, and square of this is p squared c squared plus m squared c to the 4, and square of other side is h squared nu squared plus h squared nu prime squared minus 2 h nu prime plus, I think there must be like 2 m c squared h nu prime, and also square of this, which canceled. And since we divided the entire thing with c, this one will go, so there will be actually a factor of 2 here. So this one is 2m h nu minus h nu prime, and on the other side I'm going to have 2 h nu over c, h nu prime over c, minus 2 h nu over c, h nu prime over c, cosine phi. Right? That's the final equation. We are basically done, but we want to make it just a little bit simpler so that we can use this thing. So I'll cancel these 2's. And I think, let me check if I missed anything here. No, I think that seems to be right. So I want to write C here and C here. And I want to take H outside. So let me write it like this. H outside, this one and this one. And let me, for you to not get lost, let me just copy and paste and manipulate so that we can compare. So this mu over C is going to be 1 over lambda, right? Let me write it. So this is what I'm going to use is speed of light is going to be equal to length times 1 over time, which is mu. Then whenever I see mu over C, I'm going to write 1 over lambda here, 1 over lambda prime here. And this one is also actually, so this one lambda, this one is lambda prime, this one is lambda, this one is lambda prime. Good. I think I can also cancel 1 over the h, this one, and this one cancels. Okay, good. Now I take this, okay, this is 1 over, I multiply everything with lambda and lambda prime. What I'm going to have is mc divided by h. This is the h. So multiply everything with lambda, lambda prime, lambda prime divided by lambda minus lambda, lambda prime divided by lambda prime is equal to 1 minus cosine theta. Let me check that. Okay, I think this angle should be phi because I'm taking this one. So this is phi. This is also phi. I would appreciate if you guys help with these mistakes, but that's fine. So this is phi. And the final result is I want to write it like this, h over mc. And I want to delete this. Now this is going to go like that. Cancel lambda primes. And at the end you can see I have like a very nice thing. The shift in lambda, which is lambda prime minus lambda, is given by only the angle and a constant which is h over mc. Okay. So this one, what we call Compton's formula, and h over mc is called sometimes Compton radius, and its numerical value, if you put all these numbers, I think I should have it somewhere, or it's like Compton wavelength, and it is value is equal to 2.4 times 10 to the minus 12 meter. So this is even like beyond angstrom, right? It's like order of atomic size, but it's, since we are trying to probe the electron, it's even like smaller than that. Any questions? Yes.
So can we use PC instead hash nu not?
Can we use PC instead of h nu?
H nu not.
Nu not. So we use, okay, there are two kinds of momentums. Momentum of a particle with mass and momentum of a particle without a mass. For photons, for energy of photons, we have to use h nu, right? This is photon. But if we have like an electron which has like a massive particle, we use P. Right? Whereas, okay, h nu, this is energy, so to convert this to momentum, I just divide this by h nu over c. Is that clear? Because if you remember from relativity, E is equal to P squared C squared plus M squared C to the 4. And we said even when M is equal to 0 and V is equal to C, we can use this formula, and we had P times C. From here, P is equal to E over C, and for E I use h nu if I'm dealing with photon. Is that clear? Yeah. Any other questions or comments? So are you following the lecture, or are you reading something in your laptop? Okay, good. Okay, good. I trust you. I get distracted, I have tasks. I apologize. So let's also talk about the experiment, and I'll finish this here. So Compton experiment. I think Compton both did the experiment and also explained the theory. As far as I know, I think you should check your resources, but Compton was the first person to derive this formula, and he saw that this formula was working for his experiment, which I'm going to explain now. So Compton experiment. So in the Compton experiment, what we have is, we have like a X-ray source, and you take the X-ray source and bombard. You have like again a target, right? This is target, and of course, if you could just shoot electrons in the air in empty space, you would do that. But typically, you can do that, right? You just pick a sample in which there's like a lot of electrons, and you shoot your radiation, and you hope that the effect you see is going to be the theory you developed. And from here, you have like a detector. So this is the detector, and this detector makes an angle, which is the phi we used for the scattering problem. And at the end, you have something like that. You have, as always, we always look at the spectrum of something, and that spectrum tells us about the quantum mechanics. So in this case, you have the wavelength. This is like a magic detector. We don't care. It just, if we want frequency, detectors give us frequency. If we want wavelength, they give us wavelength. And there's the intensity of radiation that comes. For this one, let me say it like this. Now, okay, the first one is, suppose I put my detector right here, right? If I put my detector here, phi is going to be 0, and whatever I shoot is just going to go through, right? The wavelength of X-ray, whatever I picked, is going to be somewhere here, and the detector is going to see all of these X-rays that just pass through without scattering. But because of like things that we cannot control, there will be like broadening of spectrum, and it's going to be something like that. Okay. Now I want to change the angle. I want to put my detector not here, but like say 45 degrees. So this is this is the location of my detector. And in that case, so we have exactly the same spectrum, but this one is going to reduce a little bit because some of them are going to scatter. But because of this Compton formula, right? Here is the formula we derived. Just put 45 here. Cosine 45 is like what? 1 over square root of 2. 1 minus 1 over square root of 2 is something smaller than 1. So lambda prime is going to be shifted just a little bit from lambda. And it is defined by this h over mc times, I don't know, 1.2, whatever the number is. that shift is going to occur here, something like that. And this distance is going to lambda minus lambda prime. Is that clear? This is 45. Yes, thank you. I appreciate. This is 45 degrees. Let me do one more. Suppose we put the detector not to 45, but say we put it in 90 degrees, like here. So this is my detector. Now phi is going to be 90 degrees. And as you see, cosine 90 is what? What is cosine 90? 0. So it's going to be 1 times h over mc, which is the maximum you can get. So it's going to be maybe something like that. And again, so this is 90. And okay, this is if you want lambda, this is lambda prime. Their difference is determined by this. You can even do it more, right? You can just put it here, put your detector here. For phi is equal to 135, it's going to be like minus 1 over square root of 2. Now you are going to have like minus something which is going to be bigger than 1. And in that case, you are going to have like even something like that. Okay?
Alright.
Yes?
What did this difference of lambda tell us?
So the difference between lambda and lambda prime tells us about Compton scattering, right? Like the X-rays are coming in, they are scattering of electrons, and we are just looking at how much, like, I know the wave I sent, I know what it is, right? Here, I know exactly what I sent, but I don't know what will come out. For this, I put like a detector. By comparing what I sent with what I got, I obtain the Compton scattering. And the Compton scattering only knows about angle, right? Only angle, and there's nothing else. Of course, there's this Compton wavelength. And because the experiment matches this, we say that, oh, okay, we are actually seeing Compton scattering in this experiment.
Does this Compton scattering tell us something about the property of something?
Not the property of material. We are like exactly whatever the material you have, as long as you have electrons that can scatter the X-ray, you are going to see the Compton scattering here. Right? Any questions or comments before I finish? All right, thank you.